12.2 of our conic sections is the ellipse. And the ellipse, we're probably familiar with its shape. It's a circle with one of the axes elongated. By definition, it's a set of all points in a plane such that the sum of the distances of P from two fixed points, F prime and F, but by the way, those are our focus values, in the plane is constant. And just like we had with parabola, we have some definitions we're going to have to work through here with our ellipse. So focus, as we have in the parabola, we also have in the ellipse, although together we have two of them there called foci. And these points are going to be inside of our ellipse when we find them. We have two axes. We have the major axis, which is the longer part, and the minor axis, the smaller part. They are perpendicular to one another. And for our ellipse, when we're centered at 0, 0, we'll be going through the origin. But these major axes and minor axes always go through the center point, wherever that might be. Vertex definition is a little different. Our vertex is at the end of each major axis. So what we have here in this diagram is we have our ellipse that is having a major axis on the x. And here we have our vertices. There's one of them right there, and there's the other one right there. Those are at the end. Those are at the end of our major axis. So that's a vertex, and then there's one over on the left. You can see the focus in the middle, and then we have some arbitrary point on our graph we call x, y. That one would be f. This would be f prime. So now, unlike a parabola where the distances that we were referring to are the same, they're not anymore. This r1 plus r2 distances is just a constant value as we spin around the ellipse. And here's the major axis, half of it. Here's the minor axis, half of it. And let's go see what the ellipse is all about. How about some equations? We're not going to come up with the derivation for these, but here we have two equations, unlike our parabola. So we have x squared plus y squared this time. Kind of like a circle, but ellipse will have denominator parts as well. So it has the a squared under the x here in this example, and the b squared under the y. And what this setup means is that our ellipse is going to be having a major axis on the x-axis. And the next example here, the next equation that we will look at, you'll have the major axis will be on the y-axis. So what happens with the ellipse equation, and this is helpful to remember in comparing to the hyperbola's equation, is that I talk about the x squared and the y squared. They're locked in place. So that means it's always going to be x squared plus y squared. But the a's and the b's can change their position depending on which axis is the major axis. So that's something to remember with regards to our equations, because these equations, this one and the hyperbola's equation, can get confused. Which one's subtraction and all that stuff. So, all right, so here we have our x-intercepts, which define our major axis. There they are on our little drawing here. Our major axis is the x-axis. The c values define our focus. And you'll notice they're written as coordinates. And then we've got our y-intercepts, in this case because we're centered at 0, 0. Our y-intercepts will be our minor axis points. Then we have this equation, c squared is equal to a squared minus b squared. And in fact, another helpful reminder, this minus is going to be the opposite of what I see in my equation, because we're going to have another equation that looks similar to this for a hyperbola, but it's going to be c squared equals a squared plus b squared. So what does this help me find, this c squared equals a squared minus b squared? It kind of looks like, and you're right, the Pythagorean thing. So this distance that we see here, a, this line that connects our minor axis point to the focus, that distance a is going to be always half of your major axis. So this length a is the same thing as the length here to here. we have this right triangle that we get. If I pull, here's a vertical part of that right triangle, here's a horizontal part of that right triangle. Then we get that A as the hypotenuse. So what we've got is, if I'm looking for C, and I knew what the major and the minor axis values were, thus A squared and B squared, I can find where the focus is. That's typically what we're going to be doing with the ellipse. Okay, the major axis length. So here's what we have to be careful of. In my equation, I have A squared. That is not the same thing as the major axis length. So the major axis length is twice whatever my A value is, and my minor axis length is twice whatever my B value is. So be careful with that. These equations have A squareds and B squareds in the denominator. All right, that's what my ellipse would look like, centered on the X, or the origin with the major axis in the X direction. Here's what it looks like going the other way. And now, again, I told you that with the ellipse, the X squareds and the Y squareds are locked in place. X squared plus Y squared. But notice now the A and the B has switched position. Now the B is hanging out under the Y, the X, and the A is hanging out under the Y. And that is because our A will always be our major axis. So sometimes we have to move where the A is, especially in this case where my ellipse is now having its major axis on the Y versus on the X. So think about that with the ellipse. The A is your major, and it will always go with the axis that is going to be your longest one here. In this case, it's our Y-axis. All right, let's take this information now and see if we can use it for either graphing or writing equations. So graph the following, find the coordinates of the foci, find the lengths of the major and the minor axes. Maybe, just remind yourself, when it says the lengths, that means we're going to do 2 times A and 2 times B. Major is always A, minor is always B. All right, we have this equation. That looks nothing like the ones we just saw. I don't see an A squared and a B squared here. I see this is something that looks expanded form. Well, we can make this look like our X squared over A squared plus Y squared over B squared. The key with the ellipse equation, back it up for just a little bit, another key with the ellipse equation is that it and the hyperbola will always equal 1. So in this problem here, where I don't equal 1, I'm equal to 25, I can make that equal to 1 simply by dividing everything by 25. Now I get to see my A's and my B's. So simplifying this, I get X squared over 25 plus Y squared over 5 is equal to 1. All right, how do I know what the major axis is and what the minor axis is? Look for the bigger number. The bigger denominator is your major axis. And we got a 25. So the 25 is hanging out with the X squared. That means my major axis is on the X. And now I'm ready to go. So if 25 is A squared and 5 is B squared, that means I square root this and I get 5. And I square root this guy and I get square root of 5. We can make that a decimal. There's our A value, there's our B value. And that's really all I need for graphing the shape of the ellipse. And then we're going to have to include in here our focus as well. And then determine our lengths of our major and our minor. So once you find A, it makes sense to just go ahead and figure out that 2A is equal to 2 times 5, or 10. There's the length of your major axis. And 2B would equal 2 times the square root of 5. And we can leave it like that, actually. And there's the length of my minor axis. So there they are, major axis and minor axis lengths. Let's talk about the foci real quick. So where does that come from? Well, in order for us to find the foci, we need to find C. And in order for us to find C, we're going to use this equation. C squared is equal to A squared minus B squared. Well, we already have A squared and we have B squared. That was given to us in the equation. So that means C squared is equal to 25 minus 5, or it's equal to 20, or C is equal to the square root of 20, and we'll simplify it radically and get 2 root 5. So, I know now what my foci are. Kind of go running out of room here. So, my foci are going to be 2 root 5 comma 0. There's that first point. And then we will have negative 2 root 5 comma 0 as my second. All right, for graphing purposes, I went ahead and calculated the 2 root 5 is about 4.5. So our major axis is 5, and that's on the x. So we're going to go ahead and put our points in at 5, 0, and negative 5, 0. Our minor axis is about 4.5. Let's see if I can get 4.5. Hey, look at that. This is approximate here. And, oops, that's not 4.5, that's 3.5. So 4.5, there we go. And now I connect those with a nice smooth curve, and I end up with my ellipse. Now let's see here if this is going to work right. Whoops. What happened? Oops. I graphed my b values at 2 root 5. That's actually twice my b. I wanted them to be at root 5. There they are. There's root 5, just past 2. All right, and then what about my focus? Focus was at 2 root 5 and negative 2 root 5. So that's the one I was about 4.5 at. So we're right about there for f prime, and we're right about there for f. There we go. So those are my 2 focus points, and I'm going to need you to do those when we graph, so locate the focus in there as well. But there's our ellipse with the major axis on the x, which means probably this one will be a minor axis on the x and a major on the y. So again, I'm going to suggest maybe you freeze right here or pause it right here and try to work this out, and then come back and check your answer. First thing we would do is create a 1. So I get x squared over 4, y squared over 12 equal 1. There's the bigger number. So that means my major axis is the y-axis now. And that means that 2a is equal to, a squared is equal to 12. That means a is equal to the square root of 12, which is 2 root 3. B squared, these would be plus minus, by the way, if we're able to go both directions. B squared would equal 4, which means B is equal to 2. Now I can go find my major axis length and my minor axis length. So twice A is 2 times 2 root 3's, or 4 root 3's. Twice B is 2 times 2, or 4. All right, major axis, minor axis. While we're here, how about let's go find C, because now we have all of these parts. Remember, A squared b squared, we don't have to recalculate those. So we get 12 minus 4, so c squared is equal to 8. Square root both sides, and you get c equal to the square root of 8, again, plus or minus, and we get 2 root 2. From the c, we know our foci. Now we're centered this time, or our axis is now the y-axis. So our foci now have 0, 2 root 2 as one of its foci points, and the other one will be 0, negative 2 root 2. And 2 root 2 is approximately 2.8. So I'm going to go ahead and put those points on here. 2.8, right about there, negative-wise, and positive 2.8, and right about there. What about my axis now, my major axis and my minor axis? All right, major axis is now on the y, and we said that was a value of, what did we say it was? 2 root 3s. So 2 root 3 is going to be roughly 3.5. So we'll go roughly 3.5. There's that first point. We'll go down 3.5. My minor axis is 2 and negative 2. So this should be our curve here, or our ellipse. There it is. All right, this next example, find the equation of the ellipse if the center is at the origin, the major axis is along the y-axis, and we've been given these different scenarios here. All right, we're centered at the origin. Our major axis for this one is in the y-axis. Let's just go ahead and remind ourselves that way. So I know that in my equation, x squared over something, y squared over something equals 1. Now, if it tells me that my major axis is along the y-axis, I know that my a squared has to show up underneath y squared. So I'm going to have this set up for my equation. They told us the major axis was 10, which means I can find a. And the minor axis was 6, which means I can find b. And in order for us to write the equations, we only need to know a and b. And so that means I can write this as x squared over b squared, or 3 squared is 9, plus y squared over 25 equals 1. There's your equation of the ellipse centered at 0, 0. It has a major axis along the y. What about a scenario where I've got a length of a major axis? We're still centered around the y-axis, or we're still having a major axis that's on the y-axis. But now I've got a distance of a foci from the center is 8. So we know we're still looking at an equation that has the a squareds hanging with the y's. We have the major axis length, which means we can quickly find a by 2a equals 14, a equals 7. But b, we don't know. We don't have any information for the major axis length. Kind of a little sketch. We're doing something like this. And that major axis length means from here to here is a length of 14, which means that's 7 and that's negative 7. And when you're drawing these ellipses, it's probably a good idea too. I did do it on the last example. Label for me your coordinates for your ellipse, or have them listed somewhere. The major axis and the minor axis coordinates and the foci. Okay, so we have this distance. Now the foci is located on the major axis. So let's just, for kicks, just call it right there and there. And this distance is that c distance. And we have that equation that says c squared is equal to a a squared minus b squared. Ah, well, if we know that the distance of our center to the foci is 8, and that means we know that c squared is 8 squared, and our a we said was 7 squared, that means we can find b. So b squared is going to be equal to I think something is a little funky here. I don't think that's supposed to be an 8. My major axis length is too short. So we ran into a little bit of an issue here. My major axis is a total of 14, which means each leg is 7. But my foci is an 8, and that's not possible. I can't have my foci outside of my ellipse, so got a little bit of an oops here. Let's change this. Let's change that to become, let's say, a 5. Let's try it that way. All right. So that would mean then this is a 5, which means this is a 5. And now we get b squared is equal to 7 squared minus 5 squared, or 49 minus 25, or 24. So b squared equals 24, so b is equal to the square root of that, or 2 root 6, plus or minus 2 root 6. All right, there we go. Now we have everything we need to be able to fill in our equation. We have a, we just found b, so we know our equation is going to be x squared over 2 root 6 squared, which we know is just 4 times 6, which is 24. There it is right there. Plus our y squared over our a squared, and our a is 7 squared, so we're going to have 49, and that would equal 1. So there's our equation of this ellipse. All right, I think we're gonna skip this guy. It's kind of like the last one we just did. Well, you can pause it here and then come back and check the answers. We're along the x-axis now. So we have 2a is equal to 50, a is equal to 25. We have 2b is equal to 30, b is equal to 15. Then we know major axis is the x, and so we're going to have a setup of x squared over a squared plus y squared over b squared equals 1. Plugging everything in. We have 25 squared is 625. And 15 squared is 225. That would be the equation for A. Length of the minor axis is 16. So 2b is equal to 16. B is equal to 8. Again, we have a distance of foci from the center is 6. So now we're less than our minor axis length here. So we should be okay. Which means this again is my C value. So I can go ahead and set up that C squared is equal to A squared minus B squared. And we'll be looking in this case for A. So A squared would be equal to C squared plus B squared. 6 squared plus 8 squared, 100, A is equal to 10. So our equation is x squared over 100, so I have to square that, plus y squared over 64 would equal 1. Major axis is the x. There we go. And our last application problem, 4x8 piece of plywood. We're going to cut out of this thing a 4x8 elliptical top. To draw the ellipse, how far should the foci be located from each edge, and how long should the piece of string be that helps you to draw the ellipse? All right, so we got a couple things here. We know that the total length of my major axis is 8, which means I've got an A value of 4. My minor axis has a total length of 4 feet, which means my B is going to be equal to a 2. So again, here's my major axis length from here to here, and here's my my minor axis length from there to there. We're obviously centering this thing in the center of this plywood here when it comes to the equation. How do we find the C value? C value is equal to a squared minus b squared. So c squared would equal 4 squared minus 2 squared. 16 minus 4 is 12, so c is equal to 2 root 3. And again, if we were to think about decimal equivalent, we're talking about 3.5 feet from the center. From the center, not from the edge. And I believe the question was, how far from each edge? So this distance here is the one that's about 3.5 feet. And if it's a 4-foot total length, or an 8-foot total length board, then we know we have another ½ foot left over between here and here. Can't even read that. Why did I do that? Here, let's do this. This distance here is what we're looking for, and it's going to be found by the A value minus our C value. So we're about a ½ foot from the edge on either side. And then what about our length of our string here? So our string, how would we figure out how long that thing is? Well, let's get a little visual. What if this point right here on our ellipse, what if we brought that point to right there at the vertex? What would our string look like? We'll call this length D1 and D2. By the way, that length doesn't change. If I brought that point to the right side where the vertex is, the string from our left focus would be going out. It would ride right on that right focus, and then it would go out ½ an inch or ½ a foot more to get to the edge of our parabola, and then it's going to wrap back around. So it looks like thumbtack, string, comes back around, back to the thumbtack. And that distance would be, well, from F prime all the way out to F. We know that this distance from F prime, actually all the way to the edge of the board, if the distance on the end is a ½ foot, that means over here this distance is also 1/2 of a foot. So we have a 7.5 foot distance from F prime to F, plus another ½ foot of string. So this total distance from here to there would be we've looped back a half of a foot back on itself. So we have the rope or the string kind of doubling back on itself by a half of a foot. So really I would have to add on to that another half of a foot, making our total length about 8 feet. Now again, we rounded to root 3, which is our C value of 3.5. It's actually 3.46. So we'd be off a little bit. There we go.